Hello guys, today's lecture is interesting but actually very hard, or maybe a little bit boring sometimes, so I'm sorry for that. So it's lecture 8.1 and we will talk about linear maps and matrices. And the main question here is the following naive question. So what is a matrix? And of course you already know matrix is this kind of array of numbers write down as a box, but why we do that? So in particular, why we multiply them according to the rule discussed. So this is the second interesting question. So why we do that? And maybe if you want to be more precise, what shall you ask about matrices and why that makes sense is why multiplication is associative. So basically the idea is that if you have three matrices and they are of correct sizes, then multiplication is associative. And you can of course prove it just opening brackets, that's very easy, but in mathematics you should be very careful distinguishing between proofs and actually understanding why something happens. So though you can open brackets and simply prove that indeed multiplication is associative, that absolutely does not explain what is behind this computation. So we will try to find a conceptual proof of this identity, which does not involve opening too many brackets, or at least not too much, and then you will see that basically the fact that matrices exist at all and have these nice properties follows from this more fundamental linear algebra ideas we talked about. So before that, let me talk very briefly what you can do with linear maps. So suppose you have spaces V and W, or maybe V1, V2, and then one can look at, so let home V1, V2 be the space, the set of all linear maps from V1 to V2. So there is no the sphere notation home, because later on in more abstract algebra classes you will see that home stands for homomorphisms, and homomorphisms are something very close to linear maps in linear algebra setting. So that's where the notation comes from. Also sometimes if V1 and V2 are just the same vector space, then sometimes people denote this home from V1 to V2 as endomorphisms. So end of V, so endomorphism, so endomorphism. So this is the same thing as a linear map from V to V, and there is another name for it which I will use actually a lot. So that's also what's called linear operator. When I just started to learn that, I thought it is a very fancy word. Whatever. So linear operator. So one has these two nice objects, all linear maps between V1 and V2, and more especially maps from V to itself. So basically, when two spaces are the same, then you can look at maps from V to itself. And then maybe the main important idea is that this thing is a vector space. So home V1, V2 is a vector space. Vector space, and of course you need to say over which field, the same field as V1 and V2. And for this you just, if you want to take L1 and L2 are some linear maps from V1 to V2, then if you want to add them, and you want to add them on a vector V, you just add these maps. So that's completely clear. And also, if you have any lambda in F, then and L is a map, so inside this home, whatever V1, V2, then lambda L of V is just a map which first takes L of V and then rescales it by lambda. That's also a linear map. I mean, that's completely a trivial observation. So if you have like a map, say xy goes to x plus yy, and this is L, then 2L, for instance, takes xy and then sends us to 2x plus 2y, and this is 2L. And then you can easily see that this is a vector space. So just all axioms hold and so on. And you can even ask what is the dimension. So dimension of the space home from V1 to V2 actually is equal to dimension of V1 times dimension of V2. And we will see it in a moment. So that's really, really easy. And you can compare it already with matrices. So remember, matrices of size nm also form a vector space whose dimension is the product of n times m. So that's because this home will correspond to matrices very soon. And also, moreover, so if you look at NV, so NV is a ring. So why it's a ring? It's a ring because you can add matrices, linear maps, you can multiply them. So if you have L1 and L2, you can take the composition. And that's also a linear map. And it's not commutative, but other than that, it's fine. And in particular, if you have absolutely any maps, composition is always associative. So axiom like this for linear maps, L1 composed L2 composed L3 equals to L1 composed L2 L3 is completely obvious, just because if you take any vector, you apply L3s and L2s and L1, it's the same thing as to apply first L2 composed with L3 and then L1. That's absolutely the same thing. That just tells you where the map goes under the composition of all three maps. So that's all the same thing as just L1 composed L2 composed L3. So what I'm trying to say is that absolutely trivially, for every two vector spaces, linear maps between them form a vector space on their own. And if you have a vector space maps to itself, form not only a vector space, but a ring. And multiplication is composition, and it's clearly associative. And also, moreover, if you have like V1, V2, and V3 spaces, you can compose a map from V1, V2 with V2, V3. And the idea is that that's exactly all the structures matrices had in lecture 6, I guess. And so this is for a reason. So the reason is that for every linear map, you can construct a matrix, and this will be a bijection. So composition of linear maps will correspond to product of matrices, and addition of linear maps correspond to addition of matrices. This multiplication on lambda will be multiplication of matrix on a number, and so on and so forth. So this is what we are going to talk about today. So let me explain that. Okay, so let me explain that. So this is the main idea, the main definition here. So definition. So let V and W be vector spaces over F, and so let E1 up to En be a basis of V, and F1 up to Fm be a basis of W. So we have a pair of vector spaces of dimension n and m, and then let L from V to W be a linear map. So then what we can do, we can take L and just see what it does to vectors E1 up to En. So for I from 1 to n, we know that L of EI is a linear combination of these guys. So let me write it down as sum AJI Fj for j going from 1 to m. So every vector of the basis goes to a linear combination of these vectors f1 up to fm. And so basically these coefficients determine the linear map completely, because we know that for every, so if E1 up to n is a basis, then for every vectors where you send them, and these are just any collection of m vectors in W, you can find exactly one linear map with this property. So basically these coefficients Aij determine completely the map. So let's write them down in a box, in a matrix. So the matrix has sizes. So this is really confusing, so let me try to do it correctly. So it has m rows, n columns, and what I do, I take in every column, I just put this coefficients of vector L of EI. So let's see. So L of E1 will have coefficients A11, A21, and so on. A11, A21, and so on up to AM1. Then I will have A12 and so on up to AM2. And then that ends at A1N up to AMN. So we get a matrix, so this is a matrix of size m times n. A little bit, so notation here is a little bit different from what we did in matrix class, so it's kind of reversed, but that's always very confusing, so let me do it like that for now. So this is a matrix of this size. And again, so how you think of it, so I will denote this matrix as matrix M of L. And so again, so basically columns of L, so ith column of M of L consists of coordinates of the vector L of EI. Okay, so that's terribly confusing, I know that. Let's immediately look at some examples. So maybe first example, for instance, let's take a map from R2 to R2, sending xy to x plus y, x minus y. So to write down, so this is a linear map. To write down this matrix, you need to choose a basis of one space and another. Otherwise, this machinery doesn't work. So let's choose here basis E1, E2 being usual 1, 0, 0, 1. And here also choose a basis E1, E2, which is just the same. So when vector spaces are the same, usually people will choose the same basis. And then what we know that L of E1 is just, so x equal to 1, y equal to 0 goes to 1, 1, which is E1 plus E2. And L of E2 equals to 1 minus 1, which is E1 minus E2. And so the matrix in this basis is, so I write down 1, 1 in the first column and 1 minus 1 in the second. So that is how it works. So here is another interpretation. So basically another perspective on that. So also very convenient to keep in mind, and maybe simpler in many cases. So choosing a basis is the same. So choosing a basis, that's literally the same as choosing an isomorphism with Fn, no, Fd, where d is a dimension. So then we can think of V. So V is isomorphic to f power n, and W is isomorphic to f power m. And again, so this is just not because if you just take two vector spaces, finite dimensional, there is no choice of isomorphism, but you can choose now an isomorphism which just identifies these vectors with vectors 1, 0, 0, 0, 1, 0, and so on. And this is a unique isomorphism. So picking a basis of V is the same thing as choosing an isomorphism with this coordinate vector space. So after that, of course, now we can think of vectors EIs, these are just vectors with 0 and 1s, and every vector has some coordinates. So then, so if V has coordinates x1 up to xn, then here is how you compute coordinates of L of V. So L of V, you just take this matrix in this basis, A11 up to AM1, A1n to the AMN. And then if you have a matrix of size m by n, it makes total sense to multiply it on the vector x1 up to xn. So just because every, so you just can multiply the corresponding row on the corresponding column and so on and so forth. And you get basically, yes, and the claim is that it's exactly vector L of V, where V is this vector. And if you just multiply, you will get A11 x1 plus TDD plus A1n xn up to AM1 x1 plus AMN xn. So, and then the question is, so you want to see that this vector goes to this vector. And of course you can just, you know, take, so this vector is nothing but sum xi ei, and so just apply this formula in open brackets. Or you can just see, for instance, that if you take as a vector x1 up to xn, the one which is 1 and 0 everywhere, when you will multiply, you will get exactly the column where you see 1 here. So for instance, if you have 1 here and zeros everywhere else, you will get, when you multiply, just the first column of your matrix. And that's exactly what our rule is. So image of EI is one of the columns of the matrix. So this is how you can prove that this L is exactly this, this map. So basically you can, and then in this example, for instance, indeed, so if you think what we do, we exactly picked here a basis, which is making this isomorphism from this vector space to R2, right? So that's exactly this 1, 0, 0, 1 basis everywhere. And so you can now see that what this rule tells you, it tells you that vector xy, which now I will write down as a column here, goes to vector 1, 1, 1 minus 1 times xy, which has coordinates x plus y, x minus y, and that's it. So, and these are exactly what this rule says. So this is how it works. Okay, so if you have seen it, if you see it for the first time, take a little break here. That's terrible, I know that. Let me, before giving you more examples and various properties of this beautiful correspondence, emphasize a very important point. So, a few very important points. So firstly, again, so a linear map determines a matrix. But if you just have a linear map and two vector spaces, you don't know which matrix you write. You need to choose a basis in one of them. In each of them. And then you have a very good rule which gives a matrix out of a linear map. Another way to think about it is that if you have two vector spaces which just are Fn and Fm, then maps there naturally can be written down as linear maps, as matrices, sorry. And then choosing basis is the same thing as choosing these isomorphisms. So you should think of a matrix as a way to present a linear map. But when you change basis, you will get different presentations of the same linear map. And the whole beauty of linear algebra is to try to understand how to choose basis in a way you will simplify the story, and you will be able to understand the linear map in the most convenient way. Last remark, I will talk about it again later on. If your vector spaces V and W are the same, so just literally the same vector space, then your map is called endomorphism, and there is a very convenient choice. You choose the same basis in both of the spaces, like E1 up to En here, E1 up to En here. And then you don't need to choose two different bases, you have this canonical choice of one basis. And this is a particularly important thing, we will talk about it later on a lot. Okay, so now let's move to understanding various properties of this map and consider a few more examples. Okay, let's consider one more example. So as a vector space, so we take a vector space which will be polynomials of degree less or equals than 2 over a field, I don't know, real numbers. So then our vectors are these polynomials, ax squared plus bx plus c. And then we can choose a basis. So choose a basis. So E1 equals to 1, E2 equals to x, E3 equals to x squared. And then, so let's consider a map from V to V. So to write down a linear map, we need to choose a basis. So basis here is in 1 up to 3, and here is the same basis. As I said, when vector spaces are the same, that's the most natural choice. And L takes a polynomial P and computes the derivative. So notice this is not defined by formula, it's kind of defined abstractly. So we know, yeah, and we want to compute the matrix. So for that we need to take basis vectors and compute their derivatives. So L of E1 is derivative of 1 equals to 0. L of E2 is derivative of x is equal to 1. L of E3 is x squared derivative is 2x. And then we can write down the matrix. So for this, we need to take L of vector E1, and this is just 0, so coordinates of it are 0, 0, 0. We can also, so this is just 0. This is 1 times the vector E1, and this is 2 times the vector E2. And so this means that here we'll have 0, 1, 0. And here we'll have 0, 0, 1, 0, and here have 0, 2, 0. So that's the matrix of our linear map, matrix of L. So the second example, maybe third example, which is a very strange example. So let's suppose we have a, I don't know, L from V to V is an isomorphism. And then let's suppose that E1 up to En is a basis of V. And then suppose that L of E1 equals to F1 and so on, L of En equals Fn. And remember, isomorphism takes a basis to a basis. So F1 up to Fn is a basis of V. And so now we can do different things. So we can take V, and take in both of them E1 up to En and E1 up to En basis. And then the matrix of L is something interesting. So this is something fun. I mean, I have no idea, it depends on the map, but that just, you need to take E1, compute, expand in a basis, write down coefficients, like anything can happen here. But if we take V and V, here we choose basis E1 up to En, and here we choose F1 up to Fn. So a priori in our definition we can take any pair of bases, nobody cares. Then of course we know that L of E1 is just F1, so the first thing is 1, 0, 0, 0, the second is 0, 1, 0, 0, 0, and so on up to 1, and you just see the identity matrix. N by N matrix with ones on the diagonal. And so basically, if you don't know which basis you choose, your matrix will not tell you that much about your map. But if you choose basis in an interesting way, it is more interesting. And if you take basis in V and the second space just to be the same basis, then that's not clear at all what you will get and what is the canonical form of this map. We will talk about it a lot later in the course. So that's something actually interesting. Okay, so now I want to talk about various properties. So properties of this correspondence. So we have a we have this correspondence. Let me remind you, we have VW, and so this has basis E1 up to En, and this has basis F1 up to Fm, and we have a linear map L. And then the question is, okay, what properties does it have? Or maybe like L1, L2, and so on. And then it has many interesting properties. So firstly, so there is a map which takes a map L and associates a matrix M of L is a one-to-one correspondence between home from V to W, which is just the set of all linear maps, and matrices. And here we should be careful. So the number of rows is equal to the dimension of W, so M by N. So why it is the case? That's completely obvious because proof. Let V1 up to Vn be the columns of the matrix of a matrix inside this M by N matrices. And then there exists a unique, so I think of these columns as vectors inside W because I use this basis to identify W with Fm. And then there exists a unique linear map such that L of EI equal to VI. That was the main theorem about linear maps. So if we have a basis here, and we have any n vectors here, which you can take this columns of a matrix, then such map exists and is unique. So for every matrix we constructed a linear map, for every linear map we constructed a basis, and if two matrices coincide, then maps coincide on the basis, so they coincide, and that's this one-to-one correspondence. So basically, you can think that there is no difference between matrices and linear maps, except that it actually happens when you have a choice of a basis. So if you think of linear maps from Fm to Fn to Fm, then actually indeed they are the same as matrices. But if your vector spaces are abstract, it depends on these choices, and so the story becomes much more interesting, which you will see later on. So, but anyways, that's a one-to-one correspondence. And then we can take all these different operations. So for instance, you can take a matrix of L1 plus L2, and that of course will be the same as matrix L1 plus matrix L2. So, that's just because if you look at the formula, it behaves in this way, so I will leave it as an exercise. Moreover, you can take, for instance, so if so if you have a L of V, if you take a matrix of lambda L, then this matrix is just lambda M of L. I mean, basically, because when you take lambda L, so what it does, it rescales all the vectors, and so you will just have to rescale all the coordinates in the matrix, and that's what multiplication on lambda is. And so this 2 means, so this correspondence, this map from end of V1 to V2 to matrices M by N, which takes a map and sends it to a matrix of L. So this is now a map of vector spaces, because this is the vector spaces we discussed in the beginning. Sum goes to sum, multiplication on number goes to multiplication on the number. That's also a matrix, a vector space. And this is a bijection. So this is an isomorphism. And in particular, we have a beautiful corollary. So dimension of this home V1, V2 is just NM, because this is the dimension of matrices as vector space, where you take as a basis just the zeros and 1 somewhere. So that's the third property. But that's all more or less silly, because like adding matrices is simple, multiplying them on numbers is very simple. So that's not too exciting. So the most important property is that of composition. So let's now look at that in some detail. That's actually quite confusing. Okay, so now composition of linear maps. That's actually the main important reason why we know how to multiply matrices and stuff like that. So let's suppose we have 3 vector spaces now. So let's suppose we have V1, V2, V3. And then we have linear map L, linear map M. And then we need to choose bases here. So let's suppose we have a basis here, which is E1 up to En, F1 up to Fm, and J1 up to J, say, K. So these are bases. You can think of it in more concrete terms, as we have a map from Fn to Fm and then to Fk. And then the composition is, of course, a map which we denote by M composed with L. First we do L and then M, and that's the composition. So then we can take matrices of these 2 maps and the matrix of composition. So let's try to see. So matrix of composition. And then we can have a matrix of M and a matrix of L. So what sizes do they have? So this is a matrix of size. So the number of rows is equal to the dimension of the image. So the number of rows is K times M. And here we have a matrix of size K times M, M times N. And here we have a matrix of size K times N. So let's see. So this one is K by N, Kn. So this is Mn. Sorry, something is... Give me 1 second. So K... Something is going terribly wrong here. So L. Sorry. So L has so L is a matrix going from sorry, that's two numbers are wrong. Yep. Okay, so M is from here to here, so it is a K by M matrix. And this one is from here to here, so it's M by N matrix. And so this is K by M, this is M by N, and so you see that it's make total sense to multiply these two matrices, and indeed we can multiply them because number of columns of the M matrix is equal to the number of rows of L matrix, so we can multiply them, we will get K by N matrix. And so this is the statement, that if we take this matrix of the composition, it is the same thing as to multiply these two matrices. And again, looking at the sizes, you can figure out the sizes of the matrices. So this is the main property of the correspondence. So multiplication of matrices corresponds to taking compositions of linear maps. So let me prove it now. So proof. So of course, if you want to prove an identity like that, you will just take a basis and apply this linear map to a basis. So let's take the linear map L first. So let's suppose that let's start with L. So let's suppose that L of EI equals sum AJI FJ. So here you should be careful. So I goes from 1 to n, and summation goes from 1 to m. So this is what L does, and so AJI will be exactly the terms of the matrix of L, which is this one. So this has terms AJI. So and the number of J goes from 1 to m, so J is the first number, so that's the number of rows, and I is the number of columns, so that stays in the position JI. Okay, so then let me do M of Fj. M of Fj. So J now goes from 1 to m, and then we sum, and this guy lies inside the space V3. So this is a sum from, we need some additional index. Ij, k is already here, L from 1 to k, so ALJ, GL. So you see, that's not terribly hard, but actually working with indices is confusing. So, and especially mathematicians are bad with that, and also mathematicians working in the board are completely terrible with that. So I'm very sorry. So ALJ, and this should be not L, but some other letter, say B. So this is BLJ, and that stands in this J's column and L's row. So then this guy has some other indices, and let me denote the index Li. So if it stays in L's row and I's column. So at least that makes sense, because I is going from 1 to n and L is going from 1 to k, so that's at least reasonable. And so then we know what is CLI. So CLI, if we look at matrices, so for matrix multiplication, we know that according to formula, so CLI equals to sum BLJ times AJI, where J goes from intermediate size 1 to m. So that what was the formula for matrix multiplication. So now let's try to see what is the matrix of LM. So assume that it has, let's compute it in the other way. So if we take LM map, M composed L, M composed L, and apply it to EI. So it's the same thing as first to take M and apply it to this vector. So sum AJI FJ from j equal 1 to M. And of course we can apply linearity. So this is sum from j equal 1 to M AJI M of Fj. And then we can plug in the formula for M of Fj. And so now we see that this equals to sum AJI. And then we multiply on the sum BLJ GL. And here the sum goes from L equal 1 to K. And here the sum goes from J equal 1 to M. So at that moment, if we made any mistake, it will be terrible. So then we can open brackets. So notice this thing does not depend on L at all. So we can actually plug it in through the sum, just because, you know, summation is associative, nothing else. Sorry, distributive. So that's equals to sum from J equal 1 to M, sum from L equal 1 to K, AJI BLJ GL. Perfect. So that's looks very close to this thing. So when we have these two summations, so notice, so this is here now we have lots and lots of terms depending on all these indices, and we are interested in the coefficient before GL because this is exactly what CL I should be. And then we just change the summation order. So L, we sum over L here, and when you have two sums, you can exchange their order just because, you know, this is just a sum of ton of numbers, and it does not matter you sum them in this way or that way. So that is the same as sum from L equal 1 to K of the sum from J equal 1 to M, AJI BLJ times GL. So this is nothing but coefficient. So notice that this is exactly C Li. So we have seen that M composed with L of EI equals to sum CLI GL from L equal 1 to K. And that means that the coefficient in the product of two matrices is exactly the coefficient, the corresponding coefficient in the matrix of the composition. So basically, and then we see that matrix of M composed with L equals to matrix of M composed with matrix of L. So that's the end of the proof. And I know it's terrible. If you will do physics or something like that, you will have like millions of computations of this type. You will work a lot with concrete bases, with coefficients, and so on. In physics, there is a convention. Usually people omit the summation sign, and so on. But so you will see all of that. In mathematics, mathematicians like to work abstractly, not to do messy computations, because they tend to not understand them. And so in mathematics, we rather prefer to talk about vector spaces, linear maps, and fancy stuff. But sometimes you need to do the dirty jobs with your hands and actually go to matrices and computations, and then you have this complicated indices and stuff. So, but anyways, of course, the main corollary is, that multiplication of matrices is associative. And now there is nothing to prove, because we know that if you have three maps, L, M, N, then their composition is associative, so the corresponding product of matrices will also be associative. And now we don't need to check more complicated identity about associativity of matrix multiplication, because we have understood their meaning. Okay, that's it. Let's move on. Okay, so maybe one last property of matrix stuff. So let's now suppose that we have a vector space V with a basis, and we look at maps from V to V with the same basis, and then let L be a map, linear map here, which, so this space, linear space of maps is called endomorphisms of V. So then the following fact is clear. So L is an isomorphism if and only if M of L is invertible. And then the matrix of L inverse is just the matrix of L inverse. So that's a very, very simple fact now. There is almost nothing to prove. Maybe one more idea is that matrix of identity map from V to V. So this is a map which does not do anything, I remind you, is of course just identity matrix. So that's because, so this identity V takes a basis E1, vector E1 to E1, and En to En, and so when you write down E1 in the basis E1 up to En, you get 1, 0, 0, 0, 0, 1, 0, and so on up to 0, 0, 1. So that's why identity matrix looks like that. So now you kind of can understand such stuff. And then this is completely obvious because, I mean, L is an isomorphism. So I mean, let me prove it basically. So remember, L is an isomorphism. Then there exists M, such that L composed with M is identity. And M is going from V to V again. So yeah, and then matrix of L times matrix of M is matrix of the identity map, which is just 1. And so in particular, matrix of L is invertible. And then you can just take if you want to go backwards, sorry, if you know that matrix of L is invertible, just, you know, take the inverse matrix and take the corresponding map, and that will do the job. So backwards is similar. That's the proof. So basically, now when you think about a matrix, say A, B, C, D, so you can think of this matrix actually, so this can be sort of as follows. You can think of it as a map from F2 to F2, which sends a vector xy to the vector, and then you take this A, B, C, D times xy, and this equals to a vector ax plus by, comma cx plus dy. So this is how you think of a matrix as a linear map. Perfect. So that was tough, but we did it. So now the last topic, which is actually probably the most confusing here, and the main goal is to understand it conceptually, is the following question. So if you have a vector space V and W, then you have this linear map, yeah. And then you can pick one basis here, but you can also end here, and then you have a matrix. Or you can take another basis here, and another basis here, and then you have another matrix. So, so the question is how the matrix of L in basis E1 up to En f1 up to fm, and e1 prime up to en prime, f1 prime up to fm prime are related? So that's an interesting question, and this is definitely important because we want to be able to understand what happens with what happens with these matrices when you change bases. So probably this will be some important operation or definition about matrices, and that's indeed the case. So let me try to explain that. So for this, we need some way to encode change of bases. And we know what is a change of basis. Change of basis is an isomorphism. So consider, let I1 be a map from V to V, sending this basis, sending such that I of EI is EI prime. So for I from 1 to n, and I2 be a map from W to W, where I2 sends Fj to Fj prime, J from 1 to M. So let's consider the corresponding maps changing this basis. So one of them is this one, I1, and this is I2. So this I1 and I2 are definitely both isomorphisms. So these guys are isomorphisms. Why? Because remember, isomorphisms are maps which take a basis and send it to some other basis. That's what all isomorphisms do. So, so definitely these guys are isomorphisms. They exist. They are unique. And then now we have, so we can do the following thing. We can look at I1, I2. We can write down their matrices in some basis. We can look at L, and we can look at this matrix of L in the other basis. So let's see how they are all related. And that's terribly confusing. So let me clean up this board so I will be able to write it down. Okay, so first we need to agree. So we will write down some matrices, and so we need to agree in which basis we write down all these matrices. So okay, so let's do everything in the basis E1 up to so let's see. Okay, so we have matrices. So we have matrix of L. So let M1 of L, let M of L be the matrix of L in the basis E1 En, F1 Fm. Just to keep in mind, so this is a matrix of size M by N. So let M prime of L be the similar matrix in the basis, and this basis will be E1 prime, En prime, F1 prime, Fm prime. And we want to understand how these two guys are related. So we can add to them two additional matrices. So we can take matrix, which I will denote, let me say matrix of I1. And this one is a matrix of I1, so in the basis where the first one is E1 up to En, and the second is E1 prime up to En prime. And similarly, Mi2 is similarly, but now we have F1M, F1 prime, Fm prime. And then the statement is that there is some identity between these matrices. So let's try to see what it looks like. So for that, let's see what do we know. So if we take some vector, let's take a vector in So let's look at this matrix, M prime of L. So what does it do? So if you take a vector written in coordinates f1 prime up to fm prime, then it will, if you multiply this vector on this matrix, you will get the image of L written in basis in this basis. So then you can apply this map and multiply this matrix and get the same vector in the basis e1 up to en. Basically this is what we will do. So let me try to do that kind of diagrammatically. So take a vector v. So you take a vector v inside W. And let's suppose you have a vector v. So vector v equal to something like x1 up to xn maybe in coordinates, in basis e1 up v in v, v in v, which equals to x1 up to xn in coordinates in the basis e1 up to en. So then we can write down, so we can take this vector v and we can multiply it on the matrix m1 of L. And this is just the vector L of v in, this is the vector L of v in coordinates f1 up to fm. So now we can take this map I2 and take its matrix in this basis, and I want to, so if I multiply on this matrix, what will happen is now I will take this vector L of v and rewrite it in coordinates f1 prime up to fm prime. So if I multiply it on M of I2, so this is now a vector L of v in coordinates, in basis f1 prime up to fm prime. Okay, but then I can do the other thing. So I can take M of I2, so I can take vector v, and this is vector v written in coordinates e1 up to en, but if I multiply it on M of e1, then now this is vector v in coordinates, in the basis e1 prime up to en prime, and if I multiply it on the second matrix M prime of L, then I will get this vector, the same vector L of v now, in coordinates, in basis f1 prime up to fm prime. So now I have two ways to write down the same vector L of v in the same coordinates, so they should agree. So these two guys are equal to each other. And so, basically the statement. So if we have these two maps with these matrices, so then we conclude that, so we know that this equals to each other for any vector. Thus the maps agree, the matrices agree. You can just check it by taking vectors 1, 0, 0, 0, and so on. So then we see that M prime of L equals to, so this matrix is invertible, so we can multiply on its inverse, mi2, M of L times M of I1 inverse. And since it's an isomorphism, it does not matter whether you take I1, M of I1 inverse or M of I1 inverse. So basically, what does it say? It tells you that to get a matrix of the map L in the different bases, you need to multiply on the left on the matrix of one of the isomorphisms which change one basis, and on the right on another matrix of an isomorphism which changes another basis. So that's what the formula looks like. And this is very important, though it's completely impossible to remember. So you need to kind of understand the logic and follow it once or twice, maybe try to write down some examples, but I don't think memorizing this formula is actually possible, to be honest, at least not for me. I mean, you can remember that M prime of L, you need to multiply on one matrix and on the other on left and right, and it's easy to see what are the sizes, because otherwise you will be not able to multiply matrices. matrices. So M of L is of size M by N, and this is hopefully M by M. Let's see. So I2 is, yeah, so this one is M by M, and this one is N by N. But to remember, when we have inverse, that's completely undoable, probably. Anyways, so this is very important, but there is one corollary of this computation which is even much more important than the computation itself. So let me give you the corollary of this statement. So for this, I will slightly modify the setting. So let's imagine that now I have, so I will erase this part because it's just a computation. So let's imagine I have similar setting, but now vector spaces V and W are just the same vector space. So let me erase this part. Okay, so let me now explain a very important corollary. So let's take the following setting. So let's imagine V and W are the same. So we have a map which is an endomorphism, L. So L is an endomorphism of V. Also, people say linear operator here. That's really useful name. And then suppose we choose a basis E1 up to En here, which is the same as here. So as I said before, that's the most natural choice. You don't need to choose two bases when you have the same vector space. So then you can imagine that you have similar kind of question, but now you have E1 prime up to En prime, E1 prime up to En prime. So you change the basis, but to the same basis again. And then, absolutely similarly, you have this I, which is an isomorphism from V to V, which sends I of EI equals EI prime for I from 1 to n. So now all the numbers are the same, and there is just one such isomorphism. And so then what we know is that M prime of L, which is this matrix in the second basis, equals to M of I, M of L, M of I inverse. And that's very interesting because, I mean, let me denote, say this matrix, suppose it is like matrix A, and this is matrix X, this is matrix say B, and then this is X inverse. So you see that what happened here is we took a matrix of a linear map and then we did what's called conjugation. You multiply it on some invertible matrix, and on the other side you multiply it on the inverse of this matrix. So definition. So matrices A and B of size n by n are called similar if there exists X also there, such that A equal to X, B, X inverse. And the notation is sometimes A is similar to B. So a priori that looks weird because you know why you call them similar, like what is the reason for that, why it's useful, but now you can firstly see that this is important because what it means that these two matrices determine the same linear map if you choose another basis. So if there are some interesting properties of linear maps, like some geometric properties, like what they do, how they change sizes, or whatever, all these geometric properties should be the same if you take a matrix and similar matrix. Later on we will talk about determinant, we will talk about eigenvectors, eigenvalues, and all these things will be related to this similarity notion for matrices. So also, you can, if you remember Fibonacci number problem in the first homework, so there was this idea how you compute the power of a matrix, and the idea was that you actually find a diagonal matrix which is similar, and then you take powers more easily in this form. And so basically this is exactly the idea we will use later on when we talk about eigenvectors and eigenvalues. So so this is why finding a similar matrix of more simple form is exactly the same thing as taking a linear map and choosing the most convenient basis to think about it. Okay, so I want to formulate maybe a few more simple corollaries and ideas. Let me erase this part now. Okay, so some more. So firstly, let's reformulate this corollary. So, if we look at, let me formulate it in this way. So there is a okay. So maybe okay. So let's look at a vector space V. And then so if V is a vector space and L is this endomorphism operator from V to V, then all matrices of L in different bases are similar to each other. So again, you should be very careful. So you choose the same basis in V here and there. If you don't do that, as we have already seen, you can get arbitrary matrix, for instance, 1, 1, 1, 1 matrix. So that's just not how you do it. And moreover, you can sort of think. So you have maybe another way to think about it is the similarity. So the similarity is an equivalence relation. And so this is something very easy. So like, for instance, we know that A is equal to 1A, 1 inverse. A is equal to X, A, X inverse, then, if A is congruent to B, then B equals to X inverse AX. This is symmetricity, and similarly you can use transitivity. And so now you can just take all the matrices, so these are all n by n matrices, notice square matrices, and they are cut into classes of equivalence. And so what are these classes of equivalence? So classes of equivalence exactly corresponds to linear maps in different bases. So these are matrices of the same linear map in all various bases. So that's the main idea, and we will talk about it a lot. So let me give you a little example of that. So example will be not actually an example, but a definition, which is very important. And so this one is a definition which is a little bit hard to understand. So let's suppose that we have a vector space V is so a vector space of dimension n, and L from V to V is a map, endomorphism, linear map. So then one can look at the trace of L is, by definition, the trace of the matrix of L in some basis. And again, I'm not yet tired to remind you that when you say that, you mean you choose the same basis here. So you have some basis E1 up to En, E1 up to En. So basically, if you know that your L of EI equals some AJI EI, then trace of L is the sum AII from I equal 1 to n, so sum of diagonal elements of the matrix. Remember, that's from homework. And so why this thing is well defined? So the reason why, so it is, this definition makes sense. So this is well defined because if you take trace of a matrix X, A, X inverse, remember trace has a property that if you change the number as the order of two matrices, you get the same thing. It's trace of X inverse XA, and then it's the same as trace of A. So that's why this trace of a linear map does not depend on the basis. You can change the basis and you will get the same linear map. So trace. So if you want to define something which is invariant not of a matrix but of a linear map, you need to take something which is the same for a matrix and its conjugate. So you have seen determinant of 2 by 2 matrix, that's one thing. Trace of any matrix is another thing. Next week we will see determinant of an arbitrary matrix, that's third thing. And moreover, there will be eigenvectors, eigenvalues, and so on. And this is all interesting stuff in linear algebra. That's exactly what it is about. Finally, you can try to understand. So linear map is doing something, it takes your vector space, like rescales it, moves somewhere, and so on. And you can ask, what is the geometric meaning of a trace? And the answer is very complicated. I mean, there are tons of different answers, and we will see some interpretations. But there is a wonderful mathematical site, Math Overflow, where this question is asked, and you can have a look at the answers there. It's about 20 answers, if I recall correctly. So trace is very important. We'll see other applications of that, and we'll see other uses of that. So thank you very much. That's the end of lecture 8.1, and in the next shorter lecture, I will talk about the notion of the rank of a matrix.